And speaking of comparisons, how does isolation forest actually stack up against traditional anomaly detection methods in different scenarios? Let's take a side-by-side look and see where it dominates and where other approaches might have the edge. Not all anomaly detection methods are created equal. Some rely on statistical assumptions, others use distance-based calculations, and a few, like isolation forest, take a completely different approach. So how does isolation forest stack up against traditional anomaly detection techniques? Let's break it down. One of the oldest methods is statistical outlier detection, which assumes that normal data follows a known distribution, like a Gaussian bell curve. Anything too many standard deviations away from the mean is flagged as an anomaly. This works well when the data is neatly distributed, but real-world datasets rarely follow perfect statistical patterns. If the data contains multiple modes, heavy tails, or skewed distributions, simple statistical thresholds can completely fail, missing anomalies or flagging too many normal points. In contrast, isolation forest doesn't assume any distribution. It works even when data is messy, making it far more flexible. Another common approach is distance-based anomaly detection, like k-nearest neighbors, KNN, or DBSCAN, density-based spatial clustering of applications with noise. These methods look at how far data points are from their neighbors. If something is too far from everything else, it's an outlier. The downside? They don't scale well. Computing distances between every pair of points becomes impractical as datasets grow, making these methods slow and inefficient for large-scale anomaly detection. Isolation forest, on the other hand, scales in linear time, making it much better suited for big data applications. Then there's one-class SVM, support vector machine, a popular boundary-based method. Instead of measuring distances or densities, it tries to find a hyperplane that separates normal data from anomalies. The problem? It's computationally expensive and highly sensitive to parameter tuning. If the boundary is too tight, it might flag too many normal points as anomalies. If it's too loose, it might miss outliers entirely. Isolation forest, by comparison, requires less tuning and runs much faster, making it easier to deploy in real-world scenarios. Clustering methods like k-means clustering also get used for anomaly detection, with the assumption that normal data forms clusters while anomalies do not. This works well when data naturally forms tight, well-separated groups, but if the data doesn't have clear clustering structures, the model struggles. Anomalies that fall within a dense cluster might get overlooked entirely. Isolation forest, by contrast, doesn't rely on clustering assumptions. It isolates anomalies based on behavior, not proximity, making it more adaptable. Where isolation forest wins is in speed, scalability, and flexibility. It doesn't require assumptions about data distribution. It handles high-dimensional spaces better than distance-based methods, and it runs significantly faster than traditional approaches. That's why it has become a go-to tool in industries like finance, cybersecurity, and healthcare. However, it's not always the best choice. If the anomalies are subtle and blend into the data, methods like one-class SVM might perform better. If the dataset is small and well clustered, DBSCAN could be more effective. The best approach often involves combining multiple models, validating results across different techniques to maximize accuracy. So, isolation forest isn't a silver bullet, but it's one of the most practical, efficient, and adaptable anomaly detection methods available today. And as datasets grow in size and complexity, the need for fast, scalable anomaly detection is greater than ever. That's why it's being integrated into big data environments where massive volumes of information need to be monitored for anomalies in real time.